The interstellar object 3I/Atlas has become one of the most intriguing astronomical subjects of recent years, not only because of its unusual behavior, but also because its recent re-emergence from behind the sun has revealed a level of complexity that challenges our expectations of what an interstellar comet or asteroid should look like. When astronomers observed the object again, they were surprised to find an intricate system of collimated jets extending outward in two directions, roughly 1 million kilometers toward the sun and nearly 3 million kilometers away from it. Such features are not unheard of in comets, yet the scale, structure, and coherence of these jets raise legitimate scientific questions about whether 3I/Atlas belongs solely in the category of natural icy bodies, or if it represents something far more unusual. Ordinarily, cometary jets form when sunlight heats pockets of volatile ices beneath the surface, causing gas and dust to escape into space. This process usually produces chaotic outflows, irregular plumes, and highly variable patterns. But 3I/Atlas displays jets that appear unusually stable, extended, and structured, sparking curiosity about whether there could be another explanation, such as artificial propulsion or engineered mechanisms. If these jets were produced by natural sublimation, the expected velocities would be only a few hundred meters per second. On the other hand, if the jets came from some form of controlled thrust, something like the exhaust from a spacecraft's propulsion system, they would reach speeds of several kilometers per second or more. Distinguishing between these scenarios is not a matter of guesswork. It is something that can be empirically tested using spectroscopic analysis. By examining the Doppler shifts in molecular or atomic emission lines from the jets, scientists can determine their velocities with great precision. This kind of measurement, taken over the coming weeks, would allow the scientific community to differentiate between a natural outgassing event and something that requires a more unconventional explanation. The beauty of science, as Professor Loeb emphasizes, lies in its ability to rely on evidence rather than preconceived assumptions or intellectual pride. True scientific inquiry demands a willingness to revise one's beliefs when faced with new data, even when that data contradicts long-held expectations. Another point of interest surrounding 3I/Atlas involves NASA's lack of publicly released high-resolution images, particularly surprising because a high-res camera aboard the Mars Reconnaissance Orbiter is capable of taking incredibly detailed photographs of distant objects. When 3I/Atlas approached within 29 million kilometers of Mars on October 3, 2025, many expected NASA to release these images promptly. Instead, nothing appeared, and NASA's website noted that any high-res images of 3I/Atlas were being withheld due to the federal government shutdown, which lasted 42 days. Curiously, the same website continued releasing new Mars surface images daily, yet singled out 3I/Atlas as an exception, stating that communications regarding this particular target were suspended. This selective withholding naturally raises questions about why an interstellar object, something of immense scientific value, would be treated differently. According to Loeb, bureaucracy may be partly to blame, but it remains unclear why intermediate datasets could not be released through alternative scientific repositories. The situation underscores a broader issue in scientific institutions: the risk of allowing administrative obstacles or communication policies to impede the free exchange of information. Science thrives when researchers share data openly, not when discoveries are locked behind procedural restrictions or slowed by internal processes. Loeb's unconventional views often spark debate, especially when he suggests that anomalies should not automatically be attributed to familiar natural explanations. Critics argue that extraordinary claims require extraordinary evidence, and that invoking artificial or technological origins should always be a last resort. Yet Loeb counters that many critics fall into the trap of interpreting new observations through a narrow framework defined by past experience. Their scientific training data, as he calls it, consists primarily of known asteroids, comets, and planetary bodies. As a result, they reflexively assume that every object entering the solar system must fit one of these categories. This is analogous to an AI system trained exclusively on a limited set of examples. It will struggle to properly classify an object outside that dataset. Loeb emphasizes that to think more broadly, scientists must expand their conceptual vocabulary to include technological artifacts, engineered structures, and other possibilities beyond the traditional catalog of natural celestial bodies. He notes, for instance, how the Minor Planet Center once misidentified the Tesla Roadster, which SpaceX launched into interplanetary space, as a near-Earth asteroid on January 2, 2025. This incident illustrates how easy it is for even experts to misinterpret an object when they assume that only natural origins are possible. Science should not be limited by habit or by intellectual inertia. If unusual features appear in observational data, researchers should explore all reasonable interpretations, including artificial ones, without fear of challenging established norms. Healthy skepticism is essential, but so is open-minded exploration. The goal is not to jump to extraordinary conclusions, but to avoid prematurely dismissing them. The implications of 3I/Atlas extend beyond the object itself because it is part of a growing pattern. In just a few years, astronomers have detected 3 interstellar visitors. 1I/Oumuamua in 2017, 2I/Borisov in 2019, and now 3I/Atlas. This frequency hints at the possibility that many more such objects are passing through the solar system, unnoticed by our current telescopes. Most of these objects are extremely small, faint, or fast-moving, making them difficult to detect. Some may pass within the Earth-Sun orbital region, yet remain invisible because they reflect very little sunlight or move at velocities too high for existing survey instruments to track reliably. The NSF-DOE Vera Rubin Observatory, now operational in the Southern Hemisphere, is expected to transform this situation. With its massive 3.2 gigapixel camera, the observatory will scan the sky repeatedly, capturing huge swaths of space with unprecedented sensitivity. Scientists estimate that it could discover dozens of interstellar objects over the next decade. Loeb argues that to achieve full sky coverage, funding should be invested in constructing a twin telescope in the Northern Hemisphere. Only then could astronomers ensure that no interstellar visitor escapes detection simply because it appeared in an unmonitored region of the sky. Even with advanced facilities like Rubin, some objects may still evade detection. High-velocity bodies, moving hundreds of kilometers per second, might cross the solar system so quickly that they do not spend enough time in Rubin's field of view to be tracked effectively. Similarly, objects smaller than 100 meters, roughly the size of a football field, could be too dim to register in the survey data. Ironically, those smaller sizes correspond to many of the payloads launched by human civilization, meaning that future interstellar detection strategies must remain open to the possibility of encountering technological debris or probes sent by another civilization. The growing number of interstellar detections reinforces the idea that our solar system is far from isolated. Instead, it occupies a dynamic environment in which objects from distant star systems occasionally pass through, carrying with them clues about their origins and histories. Each new discovery expands the boundaries of what scientists previously considered possible. The case of 3I/Atlas illustrates the importance of maintaining both methodological rigor and intellectual flexibility. To assume that every anomaly must have a natural explanation is to risk overlooking the very evidence that could revolutionize our understanding of our cosmic neighborhood. At the same time, proposing unconventional ideas should not be viewed as unscientific. Rather, it reflects the essence of scientific curiosity. Progress arises when researchers dare to question old assumptions and follow the evidence wherever it leads. In this context, Loeb's approach underscores a broader philosophical lesson. Science advances not through conformity, but through the willingness to entertain new possibilities, test hypotheses objectively, and remain open to discoveries that challenge existing paradigms. The story of 3I/Atlas is still unfolding, but it already serves as a potent reminder that the universe is full of surprises and that true scientific progress requires both humility and imagination.